bulk lead cell bulk lead cell quantum band gap is 0.3 electron volt. So, but symmetry point is the same as a bulk system. And in absorption spectra, if you look at this gamma point absorption, there are two that these absorption spectra is taken at the gamma points over time. So this Zx is the time. And so if you look at the absorption spectra, is almost similar according to with the time. So it's not changing that. It's almost featureless like plane absorption spectra is kind of like bulk system also. But at L points, if you look on this dispersion curve, they have a subgap at the L points. And due to this subgap, if at L point absorption spectra, they have one low energy peak and they have an high energy peak around here. And so when you're doing the dynamics, our main objective is to calculate for the multi-excitant generation process. So if we want a multi-excitant from the any system, we need to excite it more than two times the band gap. So then we will get it also. So in our rest of the calculation, since if you look on the absorption spectra, is they have a high energy peak intensity peak here around 2 electron volts, and that's why in all other remaining process, when I'll show you the result later on, in the initial condition we put the initial condition to excite it at around this level, around 2.5 electron volts, and this is the energy peak. And absorption spectra also showing that this is a high intensity. So this would be a favorable one. But this absorption spectra, this one is the absorptions of lead chloride, lead selenide chloride quantum dots. So the difference is the system in unit cell is same, but I make it as a quantum dots, putting the 3D confinement, but this one has a 2D confinement. So, and if you look at here, but this absorption spectra is pretty changing the shape over time. They have a pretty much it's not showing this similar localized, low energy peak. And it also, the feature is changing with the time variously, because it is maybe because of their surface also changing with the dynamics because of their open bare surface other two. It may be that's one of the reasons for this with the changing feature of the spectrum with the time. So similar as this one, I also excited this band gap is around 1.25 is compared to this one at the alpha. So I also excited in rest of the calculation for initial conditions up to here like 2.5, 2.6 electron volt. So and another thing is, and for excited state relaxation, we need to look on the all possible transitions. We want to get an overall scenario of the system. So that's why we did this excited state calculation with the 3 different conditions. I would say the limiting conditions. So limiting condition in that sense, in one condition, we choose only selective transitions, which is creating the hot hole. Hot hole means if you look on this figure, when this electron excited from the deep valence band is going to close to the LUMO band, so it will create the excited hole energy is higher than electron energy, so we denoted that as a hot hole transitions. And opposite way, when is exciting from the close to the valence band to the front orbital to the deep inside the unoccupied orbitals, so it's create the higher electron energy. Those type of transition we are saying as a hot electron transitions. And also another thing is the symmetric transitions. Symmetric transition means is hot hole and hot electron energy is comparable, so that's known as symmetric transitions. So we calculated the relaxation process with the 3 different scenarios, the limiting scenario, which will give us this following result. And this three is showing this one is a simplified figure for the relaxation pathway, electron relaxation pathway. In these two panels, these are showing the population changes with the time. This one for the nanoplates and this column for the quantum dots. And if we look at here, in this one is excited. This line is not visible. This band gap. This is the LUMO level here. This is the band gap, and I excited from here to here. And with the time, in these cases, we choose only hot in those transitions which is creating the hot hole. So that's why this whole energy is higher than the electron energy, and with the time electron is relaxing, it started to relax into the frontal orbital at 1 picosecond, and after like 2 picoseconds, whole population is transferred to the close to the frontal orbitals. And in this scenario, second one, this is for the all transition with the hot electrons. So that's the electron energy much higher. But if you compare this relaxation pathway of this one and this hole here, this electron is started to relax after 1.5 picosecond, and then is relaxed to the intermediate band. It didn't relax to the frontal orbital. It's partially relaxed but not all. And we calculated this relaxation time up to 2.8 picosecond. So it still is at the excited state, is the intermediate band. So, and this figure, this column, this is calculated the populations exactly of the band. Like for a dash line, if I go through the one by one, the dash line is including the population of hole, and solid line is indicating the population of electrons. And among them, in the black line is a population of initial condition. That means the population of that state where we excited the initially. So that's why it's pretty simple. Is initial time is 1, so it's relaxing time with the time is decreasing. And another two, red is the I consider the band, because if I look is above the figure, if you look on the dispersion curve, they have a band and sub gap on the electron orbital. So first 4, and then they have a small gap and the other band. So in the 4 state, I consider it as a 1 band. This red line is indicating that band. And if you look at this population at that band is starting increasing in this scenario, it's close to the 0.9 in these conditions. And but in this one, when I excited to the hot electron, is exciting, but after 2.8 picosecond, is close to the 0.7 percent. I mean 70%. So in this band is 70%. Still, they have some population on these intermediate bands, and these are showing by this green line. Green line is showing this band around here. So initially it's excited to the here, and but it still is not close to the 0, so it's still there containing some populations.
But you have much longer relaxation time now. So this is your old data, right?
This one that one I didn't complete the third step yet, so that's why.
But we already discussed.
Oh no, that's a quantum dot. I think this is nanoplate. This column is nanoplate, and this is quantum dot.
So you still didn't finish step 3, but you've done step 2 for longer time.
Yes. Maybe I could able to finish it maybe before printing it. So thing is, from these two limiting conditions, this I selectively or hot hole and whole electron transition is showing that the whole electron is overall relaxation process is slower compared to the hole. So that's why, and also it's because of this subgap is exciting to the relax to the here, and then it's taking time to relax to the frontal orbitals. And in this scenario, this is kind of some of these two, because I consider the all transition here around the 2.5 band gaps, and it also gives you look at here the relaxation process of this band is slower compared to this one. I mean here, the green line one. So if you look at the similar conditions with the quantum dot system, first of all, thing very significantly is observable. This showing that is relaxing to the frontal orbital very quickly compared to the 2D nanoplates. And it would be easy to, if you look at the population term, the red line, this is the populations of frontal orbital, the HOMO and HOMO -1 to HOMO -4 up to that orbital. And is in this case, the HOMO is populated very quickly, and but in electrons, this one, this red line is populated very slowly and is all populated to 1 around after 2.5 seconds. So this one limiting case, and this other limiting case is not finished yet. The one part finished, the whole part, electron part is not finished yet. But I guess if electron part will finish, it will be give us a similar result here. So this dotted line, dashed line is indicating the relaxation for population of the whole with the time. And so in this case, this one considering the all transitions, hot electrons and hot holes. And then if we look at here, because it's still is giving us the same result, electrons is relaxing slower than the hole. And another thing is, if you look at this band, this green line I calculated the intermediate bands like LUMO minus and LUMO minus 5 to LUMO minus 10. So, and initially it's excited, is populated with the time, and then at the maximum population of electron at 1 picosecond, and then it started to the relaxation. So if you look on this figure, this is very familiar graphs we did in chemical kinetics in the second order reactions. So then it is relapsing through the intermediate band, and that intermediate band lifetime is longer in case of unoccupied orbitals rather than occupied orbitals. So that's why the occupied orbital is relapsing faster from the intermediate band to the frontal orbitals, but this one is taking a long time. So overall conclusion of this figure is like the whole relaxation is relaxing to the faster in compared to the electrons, so that can introduce the in overall conclusion it will be favorable for reversal of the process because they are relaxing in a different pathway. So there was some other one. And so next question is why it's relaxing faster in compared to the zero-D materials, and in which atoms are contributing in this one. So that's why for looking on this one, I just took two different things. First figure, this one is the first Fourier transformations of bond vibrations. So we run a trajectory, and then I calculate the bond for each bond between the lead chloride, lead selenide, and selenium chloride, lead. And then I take a Fourier transform. It's giving us a vibration frequency of this one, and this is for the nanoplates, and this one is for the quantum dot. If you look at here in the quantum dot, the number is not very visible. In the quantum dot, they have a high energy frequency, vibration frequency, around 300 to more than 250 to 300. In nanoplates, they have no such high energy vibration. They have a less energy, smaller vibration around 200 to 250 or less than 150 to 200. And so what is the importance of these vibrations? To look on that, it's indirectly related, this vibration is indirectly related to the fluctuation of the band gap. So I take a look on the frequency of the band gap fluctuations. So this is in the red line, this is the black line. Black line is the frequency of the band gap vibrations, fluctuation of nanoplates, and red one for the quantum dots. So this is showing that they have a low, in this quantum dots, they have a high energy peak around fluctuation around the 300 and then 250 to 300, and nanoplates there's a smaller frequency than compared to the quantum dots. So, and in this case, this high energy peak, this black line, this is a left to right peak. So we can assume that this fluctuation, this fluctuation is arising from the left to right bond, and also is expected because chlorine is a very light element, so their fluctuation frequency is increasing higher. But because of confined, because of 2D 2D lattice, this frequency is smaller in this case compared to quantum dots one, and this higher frequency may be one of the reasons for relaxation for fast relaxation of this excitation. And so I do another things to look to kind of confirmation of this one, because and I didn't do that yet for left quantum dots. In a nanoclade, if you look at this one, is a charge density plotted projected to the z directions. Z direction is this is my cell. I mean, what I unit cell, what I use for these calculations. And there are chlorine, electron in this surface and this surface. And
what's the difference between the right and left panels?
Like you have in holes electrons, you have home luma.
What does it mean?
Whole electron means this is the initial excited state, density of the initial excited state orbital, and this homoluma is the frontier orbital of this one. And this projected to z direction sum over the two x and y, so it's giving us some information about the contribution is coming from which region, which atoms.
Again, this is at 0 Kelvin. Is it averaged over ensemble?
The average over ensemble.
Both home and luma and your initial one. Okay. So
So
it means
it's
it's a 300 Kelvins kind of average distribution for over the ensemble.
So you compute the distribution at each time step and then add them together?
And project it to the z directions.
Wait. First project it to z direction and then average.
And then added them together.
If you would take part charges along trajectory,
you're right.
you will kill the computer.
But maybe it's much easier just to look on your home luma without any average, or maybe at 0 Kelvin, just to see how it's
so I'll take homoluma orbital address and put a note here. I'll calculate the part charge and I also put some homoluma orbital.
I would suggest you just do it at 0 Kelvin to see how much your thermal kind of motion is changing this picture. Maybe it doesn't.
For nanoclouds, I have those pictures. For quantum dots, I didn't do that yet, so I need to take the image problem. And that also gives us information of what the is localized. Is it localized on the chlorine or maybe that's why? And this also giving us information where electrons is mainly they have a significant contributions coming from the surface atom. Surface means if they have a chlorine atom scale. So it's giving us this kind of. But in case of hole, in contribution of chlorine is smaller than electrons. So that's why in this case the whole HOMO and LUMO, the whole LUMO is mainly contributing from the surface atoms. So surfaces there have in surface atoms there have 6 chlorine, is 12 chlorine with the lead and selenium. So this kind of sum of all of them. And I will take the orbital figure. Then in orbital case it will be help us to look on the if that orbital is contributing coming from the chlorine atoms.
Well,
again,
this figure makes me completely crazy. So you have the black one is projected chlor charge, the red one is total charge density. But then why your red is smaller than black in some cases?
Oh, that intensity is arbitrary units, yeah, because of the populations of the lead and total charge is not the same. So,
but then it's not very much useful in the sense that if you then we cannot even say anything about really percentage of this chlorine.
Yeah, we cannot compare with the total charge, but we can compare with this contribution of this chlorine from the bulk to the surface, this kind of things. Yeah.
Why not just normalize it on the number of atoms, right? You kind of know how many atoms you have in each layer, right?
Mhm.
So then you can really kind of, based on your Z divided by this, or number of atoms probably is the same in each layer, right?
No, it's not the same. In the middle two layer, they have a maximum number of electrons. So they have the
Well, for your total charge density, you can divide, well, either think about like really going layer by layer and having division by different numbers, or you just have a just total number of atoms for the total case and just divide by how many, 68 or 100, whatever it is.
172.
Yeah. So, which of course makes your total dose immediately smaller, right?
Mhm.
And then you divide it by the number of fluorines, which are definitely much less. And this would be probably more reasonable rather than put it in an arbitrary kind of scale, right? And then they probably become visible after you, because even if your fluorine contribution is really small, because you have really few fluorines, but you divide it by small number, while total is divided by huge number, I guess then they will be visible and would have physical meaning in terms of comparing the intensities.
Yeah, that's one.
And you
We
can do it
compare
just
the
in
total
origin,
charge,
right?
yeah.
It's really very quick fix
Mhm.
to your data. Because right now it looks very strange that your total density is less than chlorine contribution.
Yeah, that's all. Yeah, every time when I describe someone, I will always mention that this is not the comparable, but we can get an idea what is the portions coming from the surface and portion coming from the middle of the slab. Yeah. So I just put the conclusions on the word. So conclusion is kind of the first effect of the confinement, because the confinement from the 0D to 2D, it's helped to control the left chloride frequency, and ultimately it will help to slow down the relaxation process. So it means non-edited relaxation, because that's non-edited process. And slow down this process means it will increase the probability of the reverse Auger process. And another this is the first, and another next conclusion, another point is, in both cases we saw that the hole is relaxing slower compared to the electrons, and wherever we excited to the higher hole, or whatever we consider the hole or electrons. So that means they have a mismatch of the relaxation process of the hole and electrons. It also favorable for the multi-acceleration generation process. And yeah, these are two mainly conclusions, and also we can talk on this main two actually. I need to look on those are not that conclusions.
That's it?
Yeah, just say it about this.
Okay, but thank Chabot. Where, at which K point the relaxation is quicker? Gamma, L, or something else?
It has a gamma.
And which figures
It doesn't
help
show.
that?
I didn't show the gamma here because.
But actually, if you compare your gamma is quicker than in it was in his old poster. That's why I guess he didn't add it. Gamma was quicker comparing to L point for the plates, right?
Mhm.
But if you compare the relaxation of gamma versus the quantum dot, which one?
That will be
comparable.
That will be comparable, I guess.
So same time.
Same time, almost same time, yeah. And gamma point is because if we look on the band, these bands are very continuous compared to the L points. So that continuous is giving us a higher coupling between the bands, so it's relaxing faster. But in L point, they have a subgap. This subgap is make this zero order relaxation to the kind of second order relaxation. Then it's relaxing to the subgap, and then it takes time to relax to the frontier.
Oh, you still have subgap in gamma point, right? For electrons especially. Maybe not so much for holes, but for electrons they are kind of split at levels. It's a different splitting, but
It's different.
they're not completely dense,
Hmm.
right? So you have your low energy state still split.
But if you look on, I mean, look, if you look on here, this is a degenerate, there are more degeneracy here compared to the gamma point. So gamma point is, I mean, this not clear subfield as the point.
Well, they have a smaller splitting, but
Yeah.
it's still not a completely dense state, completely dense contribution, right? So you expect that your confinement should make the density of states being more discrete in case of quantum dot comparing to the nanoplates. But looking on your dose, it looks like it's a backward behavior. You have more spread dose and projected dose in quantum dot rather than in nanoplates. What is the reason? Can you explain this contradiction in what you expect?
For nanoplates, or
Yeah, if you look on your nanoplates versus quantum dot, right? It looks like any of the spectra having more discrete peaks, okay, more clear peaks comparing to the quantum dot. But the confinement should make the splitting between levels more significant. So you expect these peaks being more narrow and more discrete in case of quantum dot rather than nanoplate.
It's maybe because of this is the positive dose for lead only, but this is not photon dose.
The same for the H of them, showing these very, very clear peaks. While in case of your quantum dot, right, they are more smooth, more spreaded.
Oh, this one is taken at the L points.
Still, the question is.
So this is part of this. I mean, this gap maybe did because of that subgap. Because, but I'm pretty much sure at the gamma points it was also smooth like quantum dots.
But then why is it so, like, if you look on the bulk, where you apply the 3D, like you will apply the period boundary conditions in all three directions, I think you probably will not expect that your levels will be so much discrete, right? Because this discreteness in your L, even in the L point, well, I understand L is more discrete than gamma, but this discreteness probably will be significantly reduced if you have bulk, and here you have confinement all in one direction, right? So, but in quantum dots you have all three directions being confined, right? Then, any other reason rather than just saying that, oh, just because of the L point?
No, I don't have anything.
And if you think about the surface of quantum dot, comparing to the 2D structure, which is more flexible?
Quantum dots.
So what makes this like? Ideally, if you have really spherical quantum dot with a fixed crystalline structure, your bands, I mean not the bands, your dots would be very sharp peaks, very discrete sharp peaks, right? But because the surface is even putting the ligands there, right? Your surface is not really having exactly the same symmetry as it was in a core of the crystal, bulk crystal, right? You have surface effects, some kind of destructions,
surface reorganization.
Reorganizations, right? Which kind of breaks this degeneracy in levels and because of the break in symmetry. Because your quantum dot doesn't have such a nice symmetry of bulk structure anymore, due to the surface effects.
Then,
right? And again, you can clearly see it in this when at zero kind of temperature, right? When you have applying this to the nanoplates, and this is for just optimized quantum dot, right? And you already see that this definitely has much less symmetry comparing to your nanoplate, right? And of course, losing the symmetry of the crystalline structure will having disorder on the surface, right? Losing the symmetry means you really having a disorder on a surface. Results on a kind of smearing this nice discrete peaks.
But then why we always say that increasing the confinement is making the band is
It's ideal.
Is ideal here.
Yes. Plus, you still have some selection rules because the spectra
is really very discrete. Like you have very nice discrete, well
Discrete.
resolved peaks
Peaks, yeah.
for the quantum dot.
Mhm.
Although your spectra is still very dense, right?
Mhm.
It's because although they're dense, they're optically not active. In a bulk, you have the spectra like this.
Yeah, and then like down.
They're all not very active and they all contribute almost equally. Means that you have in this very kind of broad spectra, very similar to your gamma point contribution.
Oh, that's why this transition aspect of the time also is not a uniform response. The quantum dot is
It's more flexible again,
yeah,
right?
it's creating
This
the
time you
field,
have more
yeah.
motion, more thermal motion on this, mainly from a surface.
Mhm.
The core probably is kind of restrict in the same way as your periodic boundary conditions applied to your lattice along 2 dimensions for the nanoplates. Right? Yeah. So that's why you have more disorder there comparing to the nanoplates. And again, discreteness overall, it looks like you have this discrete peaks in the spectra pretty much not very different from the L point spectra, right? Yeah. It's probably just because we really, I would say, we really need to include more K points in the 2 dimension. Then you probably will be not as discrete anymore. But confinement, like 1-dimensional confinement, of course, should contribute some splitting in levels, right?
Yeah. Okay.
I have a comment about equation 4. Shouldn't that be a sum over m on the right hand side of equation 4?
Which number?
4. Equation 4, right hand side, sum over m instead of k.
Yeah. Look, you have on the right side, on the left
Is it
side, you
left?
have an index C, P, K.
Mm-hmm.
So means your right side. Because if
Oh,
you
okay.
if you sum over K, you lose in your index.
Plus, if it's sum over k, why is CPM inside the sum?
Yeah.
Just
Does make sense or not?
You see what it is,
Yeah.
right?
So you check again. You can either change your K on the right,
Yeah,
on the
on the
left
right,
to
yeah.
whatever, but be careful, right? So it has to keep the same indexes, and if you sum, you lose in the index, and yeah, you also have this Km in your not only C but also D.
I have a provocative question. So at your equation 5,
Very good equation.
your left side and right side are matrix element times momentum on the left and only the matrix element on the right. So what is D sub Km?
That's giving a coupling between these two phi k and phi m.
But on the right,
What is your question again? Repeat your question, I didn't get it.
it's not yet a question.
Ah.
But on the right, you have only derivative, only the coupling. So why do you multiply coupling times velocity times momentum on the left?
Isn't it momentum dependent because of its not momentum?
What is momentum?
No,
R
it's not
R
momentum. dr.
with dot.
Isn't it d dr d?
Momentum of what? Your R dot, momentum of what?
Momentum of electrons?
Is it?
Oh, really?
No. Momentum of
What else you can have in your system? If it's not electrons, then what is it?
is excitement? Is the whole?
Are you talking about non-abelic couplings? Are you talking about non-abelic couplings? So what is
Yeah.
coupled in non-abelic couplings?
Is it two bands?
Huh? Exciton coupled with electrons. Are they? Excitons
No.
coupled with holes. Electrons coupled with holes. This is what we
Mhm.
call non-abelic coupling.
Mhm.
Ooh.
So
It's another,
that's
it was
momentum.
another provocative question. Be careful.
Just a
Maybe I didn't get.
Ben was hearing all the story about non-diabatic couplings for the entire summer, right? Didn't have any ideas what is it and how is it and what all this talks about in the very beginning. But I think even he probably can give you some hints. What do you remember from all these talks? What do you really call the non-diabatic couplings? What is coupled in this non-diabatic couplings?
Good question.
No answer? Okay, we pass you, then we go to London, who is undergraduate student.
It would be the electronic states that are coupled
To?
to the atomic motion.
Hmm?
Yeah.
You agree? So then, so what is your R dot? It's a momentum of what?
Is momentum.
Momentum, what the?
If your electrons coupled to
Vibrations, yeah, I mean positions of, isn't it?
of
dr
atoms of nuclei,
Mhm. Isn't it the dr is a change of the position of nucleus?
yes. So it's momentum of nucleus. It's a motion of nucleus in this case.
R dot is momentum.
But what is your d
Is
small
R dot
km?
That's why I got confused. The R dot is a momentum or is a
It's momentum
change
of
of position? I mean, in
Well,
number.
velocity.
it's velocity or momentum of
okay.
of nuclei, not excitons, not electrons, not holes.
Okay.
And small d
What is small d?
It's giving us a probability of transferring this momentum to this momentum.
This
In
momentum
other words,
to
it's
this
coup-
momentum.
I mean, in other words, it's a coupling. Of
But
these two states.
returning back to Dmitri's question, you have what you have on the right you also call coupling, non-diabatic coupling. And what you have on the right, but only one part of it you also call coupling.
On the left,
How is it
you
possible?
multiply by velocity on the
Yeah,
by
because
momentum.
phi m we are getting after change of this R momentum, phi m. Because phi k and phi m,
Uh-huh.
I mean these two are functions
Uh-huh.
are related to this momentum because we are getting this work function by changing the nucleus position.
Okay, it is not. It is
on
not
your
wrong.
right side, your phi here, right? What does depend phi on your right side
This phi depends on the nuclear positions.
only? And phi, what is the phi in this equation? On the right, where you take derivative.
These are quantum orbitals. I mean, this.
So it's quantum orbitals, which depends only on the position of nuclei.
No. I mean, is there?
When you solve Schrödinger equation, you solve it for which particles?
For electron polynomial.
So then your phi is quantum orbitals of electrons,
Also,
right? So
yeah.
then they should depend, but electron has what? Has also, well,
Well,
because it
the
moves,
nucleus,
right?
yeah.
So it changes the coordinate as well.
Mhm.
So it should depend on the coordinate of the electron.
Mm-hmm.
However, if it's coupled to nucleus, also should feel the change in position and motion of nuclei as well.
Mm-hmm.
So your right side has both in this phi. They're not, how to say, decoupled yet. Your phi depends on a position of electron, because it's quantum orbital of electron. Of course, it should depend on the position of electron. And you kind of do it in a parametric way at specific position of nuclei, right? So your phi with, at that moment of time, depends on this geometry, right? Your phi at the other moment of time depends on the other geometry. So technically, your phi has both contribution from nuclei and from the electron. But on the left, you kind of separate these two contributions. You have your product, R dot product, just for nuclei, right? So it just depends on the nuclear. And your D stays, kind of, will have a physical meaning of how the electronic degrees of freedom, means your quantum orbital, which just depends on electronic position, right? Feels any kind of change in motion of nuclei. So it's kind of the same thing, you just represent it slightly differently, kind of decouple the position of nuclear from the overall equation. And you can, I think it was again London who was doing this exercise when you were presenting your presentation a couple weeks ago, right? Showing that you can go from left to right, from this way representation to the other way of representation.
So can you write a equation for d sub km without multiplying by r dot?
Without one.
Uh-huh. You can tell by words what it is.
Km based on the basis quantum orbitals, or
Okay. So your d will have like your dk.
You can write it on your little whiteboard.
dkm equals probably 5, which you already use as a Kansham orbital. That's it?
no, I'm just saying because constant. Can we separate them together? I mean,
Can you write it down on this little
There's a
white?
small board there. You can write it on a small whiteboard. Oh, if you want, you can use a touchpad, but I'm not sure.
It's not hard. Do not hesitate.
The hint is, if your right side depends on small r and big R, and you need to take a time derivative, right?
Mm.
Chain rule or wherever, pretty much the same exercise as was done by London.
is it not sure I'm gonna do it. Okay.
Very interesting. Very interesting. What is there?
He's trying to see what you're writing.
Can you show it to us?
No, he doesn't want to. She's
I'm
hiding.
not confident of that is okay.
But we can help
Is
you.
it something like this one?
DRDT. No.
What?
No.
How you get it?
Yeah.
So just think about, on the right side you have this matrix element, right? Look only on the right side of your matrix element from the right. Means take derivative of the Kansham orbital phi, which you know depends on small r and big R.
Mm-hmm.
Small r, coordinate of the electron, and big R, the coordinate of the nuclear.
Mm-hmm.
And you need to take a time derivative. Each of these variables also changes with time, right?
Yeah.
And you need to take a derivative of the function of two variables, each of them depending on time. Oh, I can see it.
You're hiding it from Joe.
No. On the right side there is a time, and on the left.
I mean, it's not.
Oh.
It's a kind of chain.
I can see it also.
Well, the chain rule is right, but what is the answer?
Oops.
Your R dot is already having your time dependency
Mm-hmm.
as a derivative, right?
Uh-huh. Now I see what. Yes, at least the beginning is okay.
It's like,
No.
oh, it's going down. Yeah.
Okay.
Maybe someone else can help. I don't know. Erin.
I have another guess, I guess. Is
Oh,
kind
we
of
have
the
another
possible-
volunteer.
Yes.
Is that-
Yes.
Okay,
Yes.
cool.
Yes.
Do you want to help?
There it
him?
is, one of those two.
Maybe give some hint or something. Maybe he can catch it.
Sell it to him.
How much would you pay?
Oh, I know. It just memory changed. I just forgot that I do that before. on the free sticker.
I mean, I could use $20 if you want to.
And
Just imagine this is a question for your exam when you are defending your PhD.
yeah, I
Very
mean,
embarrassing, right?
No, I did this type of question before. I just took it from the code. It's something
This
else
would be
with
the
this
normal
one,
way
right?
to say that, right? Or is that not right?
It's not
Kinda.
wrong, but it's
Okay.
it's sufficient just to say matrix element of gradient. London, show it to us. Except
Okay.
we can enhance a little.
Resolution is not good enough. Okay. Theoretically. Otherwise, we never end up.
Yeah,
Oh,
please show it.
I kind of wrote.
Oh, just explain by words.
So.
Yeah, but then how do you get the DDR from the DDT?
It's not
That's
question.
a total derivative. This is a partial.
The
Oh,
div-
partial.
So that comes out of the chain rule with
Okay.
respect to big R.
Yep. Okay, but
can you write it down with yourself?
After you know what would be the right answer. And
R?
may I ask you, after, I don't know, find some time and really teach him how to do it? Because I doubt that he really got it.
no, I got it. I did that before. That I
Okay,
remember.
okay.
So-
Show it. Please show it to us.
This one?
Yes, yes, excellent. So it is definition of this little d sub km.
Yeah.
So again, the derivative is taken with respect to
Position of
Nuclear.
excellent. Yes. So now the question.
So you have time derivative in your r dot, right? Like in your nuclear, which depends on t, and dk is now just showing the change of wave function with respect to the motion of nuclear. Kind of, we already said it by words. We just need to put it in a formula. That's it.
So in your calculations, you practice your program derivative over time. Why don't you literally compute d sub km? Why don't you take derivatives over elongation of atomic positions? For example, Dan is doing so, at least in his groups.
What are you doing again?
And Andrei, they are for looking for dynamics of electrons. They also find non-adiabatic couplings, but instead they take derivatives of wave function over positions of ions.
Because of this real transition energy is reorganized the
Huh?
geometry. Because with the time during the relaxation process is also reorganized the geometry.
But if the atoms oscillate harmonically,
But it's
Then-
not a harmonic oscillation.
oh yes, so you are using your approach because your atomic motions are not harmonic.
Actually, it can be harmonic as well. Nothing wrong to be
So
harmonic.
your
Your
approach.
works for either harmonic or unharmonic.
So it is a little more generic because it will work for an unharmonic. Good.
You have normal modes.
Well, normal modes are only for harmonic, but if it is some,
If you have non-adiabatic,
Yep.
you look normal.
if like chemical bonds are formed or broken, then it is definitely not unharmonic. Okay, excellent. Anyone wants to please jab it with more questions?
or comments or suggestions, not necessarily questions, right?
Or expression of excitement. How much I like this poster. More questions. One?
Is there
Good.
electron? Is there excitonic effect?
No.
Electron?
We consider this separately. Different. So
I
this
know
is
that
the
TVFT magic had some excitonic effects.
Oh, we're not applying T.
We don't.
It's not linear response to D. So like again, the sign dependent equation for the constant equation over the Schrödinger equation, right? But we're not really imply the linear response of interacting with a perturbative interaction with a light oscillating field. So this is not included in this technique at all.
So this is the main term, right?
Mm-hmm.
Yep.
So done?
More questions
Let's-
one, more questions two, more questions three. Let's thank Jared once again. Oh, I like the way Daniel is applauding. Can you show it once again? He always did it this way. Okay.
Well, in Germany, and I think this is what people sometimes do in physics department. Instead of uploading, they just do this. No?
When we came to Germany and attended the seminar, we thought like it is a scandal. Something is wrong because instead of applauding, people knocking, telling maybe it was very bad talk. But they're knocking on the table. Well, meeting is dismissed.
Yeah? No one is
No,
showing
no.
anything else?
No. Unless there are random volunteers. No,
Very random.
no random volunteers. So please consider to complete posters, and we will have really quick squeezed session on Tuesday. Almost everyone will show for like 10 minutes. And
And Daniel, are you also going to ACS or not? You don't?
Dane.
Diana means.
Yeah.